Welcome back to our channel. Today, we're diving into a mind-blowing discovery made by the largest observatory ever constructed. Imagine a structure so powerful that it can peer into the deepest parts of space, unveiling secrets that have eluded humanity for centuries. Well, that's exactly what just happened. Scientists have detected something astonishing, something that's shaking the very foundations of our understanding of the universe. Stick around, because by the end of this video, your mind will be racing with possibilities. Let's get started. When you tune into the universe with the right tools, you'll find it's humming everywhere you look in the sky. But here's the twist. Space is a vacuum, so sound can't actually travel through it. So, what's this hum? It's not sound at all. It's the whisper of gravitational waves. If you're familiar with space discoveries, you've probably heard of the cosmic microwave background, CMB. This faint glow of microwave radiation, discovered decades ago, is the afterglow of the Big Bang itself, a key piece of evidence that secured the Big Bang as the leading theory for the universe's origin. However, the CMB has its limits. Even though it's the earliest light we can observe, it was emitted a whopping 400,000 years after the Big Bang. So what if we want to look further back, to peer into the very first moments of the universe? For that, we need more than light. We need something even older, the ripples in the very fabric of space-time. Fast forward to 2023. Astronomers from the Nanograv collaboration have announced something groundbreaking. They've used an ingenious technique to detect these elusive ripples, gravitational waves, by turning pulsars, super dense, rapidly spinning stars, into a galactic-sized gravitational wave detector. The result? They've measured the faint, steady hum of space-time itself. This hum might be the echo of the universe's birth, the reverberations of creation. I'm Alex McColgan, and you're listening to the Astron Podcast. Today, we're diving deep into the mysteries of gravitational waves and the cutting-edge methods scientists are using to detect them. You may have heard about LIGO, the laser-based detector that's famous for measuring tiny changes in tunnel length caused by passing gravitational waves. These waves stretch and compress space-time, altering the time it takes light to travel through the tunnel. However, just like light and sound, gravitational waves come in a variety of frequencies. And LIGO? It's only designed to catch a specific range. LIGO has been a game-changer in detecting gravitational waves, but its reach is limited to one part of the spectrum: high-frequency waves. These waves come from extreme cosmic events, like binary star systems spiraling toward each other at mind-boggling speeds, completing hundreds of rotations per second before finally colliding in a cataclysmic bang. But here's the catch. LIGO can't detect the early stages of these binaries. When objects orbit each other at greater distances, their orbits are slower, producing low-frequency gravitational waves. Instead of a dramatic bang, these early-stage binaries emit a faint, continuous hum, a collective signal that builds over time. The biggest contributors to this cosmic hum? Supermassive black hole pairs. These colossal binaries formed from black holes, billions of times the mass of our sun, are rare, but when they do form, they leave an unmistakable mark on the universe. Their origin? The merger of galaxies. When two galaxies collide, their vast interstellar spaces allow them to pass through one another with little direct impact. Stars, planets, and other objects rarely collide, but their gravitational forces pull everything together, eventually forming a single unified galaxy. At the heart of this newly merged galaxy, the supermassive black holes from each nucleus begin orbiting each other, creating a binary system that can last for eons after the galaxies appear fully merged. These colossal remnants of galactic mergers produce the strongest signals in the ultra-low frequency range, right in nanograv's sweet spot. However, much like the human ear can't hear ultra-low sounds, LIGO is deaf to these slow, deep cosmic vibrations. If we could listen to this low-frequency hum, we'd unlock a treasure trove of insights: how galaxies merge, how supermassive black holes evolve, and the secrets of the universe's earliest moments. Let's quickly revisit the cosmic microwave background. CMB, the oldest light we can observe. This afterglow of the Big Bang is critical, but it only takes us back to 400,000 years after the universe began, a time when the universe was still too dense for light to travel freely. For a glimpse into what came before that, we need more than light. We need to listen to the ripples of space, time itself. And the gravitational wave background? That could be our long-awaited window into the birth of the cosmos. In the earliest moments of the universe, it was anything but clear. Back then, the universe was opaque, a seething, chaotic sea of particles with far too much energy to settle down. Electrons and protons were zipping around so fast that they couldn't combine to form neutral atoms. Instead, they existed in a supercharged state of matter known as plasma, the same stuff that fuels the blazing hearts of stars. In this plasma-filled universe, light was trapped. Every photon, the particles of light, was constantly colliding with electrons and protons, absorbed and re-emitted in a never-ending cycle. Light couldn't travel freely. It was stuck, bouncing endlessly within the dense plasma. Then, everything changed. As the universe expanded, it cooled. Eventually, the protons and electrons lost enough energy to combine into neutral hydrogen and helium atoms. With no charged particles left to block its path, light finally broke free. In that moment, the universe became transparent, and this first liberated light has been traveling ever since. However, as the universe continues to expand, this ancient light has been stretched, redshifted into longer and longer wavelengths, transforming it into the faint microwave glow we now call the cosmic microwave background, CMB. This glow is the oldest light we can see, offering a snapshot of the universe about 400,000 years after the Big Bang. But there's a deeper layer of the universe's story, one that light alone can't tell. Enter gravitational waves. Unlike light, gravitational waves aren't made of particles. They're ripples in the fabric of space-time itself. Plasma poses no obstacle for them. From the very first moments of the Big Bang, gravitational waves have been free to travel unhindered, carrying with them a record of the universe's earliest moments. Even if these primordial gravitational waves were originally high frequency, the vast expansion of the universe would have stretched them into ultra-low frequencies over billions of years, similar to the gravitational waves produced by supermassive black hole binaries. Together, these different sources create what's known as the stochastic gravitational wave background, a steady hum of waves spanning a range of low frequencies. The question now is, how do we unlock this cosmic treasure trove? Could we build a more advanced version of LIGO capable of detecting these massive low-frequency waves? LIGO works by sending two laser beams down long, perpendicular tunnels. Mirrors reflect these beams back and forth, and if a gravitational wave passes through, it causes the tunnel lengths to shift ever so slightly enough to create a measurable difference in how long it takes the light beams to return. But while LIGO is incredibly precise, it's tuned to higher frequency waves. To capture these ultra-low frequency gravitational waves and reveal secrets about black holes, galaxy mergers, and even the birth of the universe itself, we'll need a new approach. And scientists are closer than ever to making that a reality. At LIGO-2, laser beams are sent down long, perpendicular tunnels, bounce off mirrors at the ends, and return to the starting point. By comparing the beams, scientists can detect distortions in space-time. If one tunnel is stretched or squeezed by a passing gravitational wave, the change can be measured against the unchanged beam in the other tunnel. But there's a problem. To detect ultra-low frequency gravitational waves, like the ones produced by supermassive black hole mergers or even the earliest moments of the universe, LIGO would need arms far larger than anything we could ever build on Earth. Here's why. The frequency of a wave is inversely proportional to its wavelength. Ultra-low frequency waves have ultra-long wavelengths, meaning their effects can only be noticed over vast distances. For example, a wave in the nanograv range has a single fluctuation that takes 1 billion seconds to complete. If we do the math, wavelength equals speed of the wave frequency, we find that these waves have wavelengths around 1017 meters. So, we're talking about waves with wavelengths tens of light years long. Clearly, building a detector large enough to measure these waves isn't just impractical, it's impossible with current technology. Even if we expanded beyond our solar system, we wouldn't get close to the scale needed. So, how can we detect these colossal waves without waiting for humanity to become a spacefaring civilization? Astronomers at Nanograv have come up with a brilliant solution. Use pulsars. Pulsars are ultra-dense neutron stars that spin with incredible precision, emitting beams of light from their magnetic poles. As these beams sweep across space, they reach Earth at regular, predictable intervals, like cosmic lighthouses. Their timing is so precise that they act as natural clocks, keeping time across vast distances. By observing multiple pulsars scattered across the galaxy, astronomers can create a kind of galactic-scale interferometer. Instead of using laser beams and mirrors like LIGO, this system uses pulsars as the mirrors and their light pulses as the signals. These pulsars are spread out over thousands of light years, forming a massive imaginary detector capable of picking up the faintest ripples in space-time. Nanograv's innovative technique essentially turns the galaxy into one enormous gravitational wave detector, using the stars themselves to help us listen to the whispers of the universe. And with this, we may finally be able to unlock the secrets of black holes, galaxy mergers, and the birth of the cosmos itself. You might be surprised to learn that the key to unlocking the mysteries of gravitational waves involves something we've been using for decades: good old radio telescopes. But the success of this method depends entirely on the precision of our observations. To make it work, we need to carefully select the right pulsars, those rare, ultra-reliable cosmic timekeepers. Astronomers hand-pick these pulsars and form a specialized group known as a pulsar timing array, PTA. For Nanograv, they've selected 68 pulsars based on a few key criteria. First, they had to be spread across the entire sky, so we can observe how gravitational waves distort space-time in all directions. Second, they needed to be millisecond pulsars that spin incredibly fast, completing hundreds of rotations per second. These fast spinners are exceptionally stable, with their pulse regularity rivaling even the most advanced atomic clocks. In fact, they're some of the most precise natural clocks in the universe, making them perfect for measuring tiny shifts in space-time over long periods. This stability allows astronomers to track the timing of their pulses over years, checking for any variations that might signal the passage of a gravitational wave. Of course, there are plenty of reasons pulse arrival times might fluctuate. Some are predictable, like changes in distance between Earth and the pulsar as both objects move through space. These are easy to account for. But then there are the unpredictable factors, like random fluctuations in interstellar gas that can delay the pulses. These variations aren't caused by gravitational waves, so how do we filter out this random noise when the pulsars are thousands of light years away? The answer: statistics. By comparing the signals from pairs of pulsars in the array, astronomers can isolate the gravitational wave background from random noise. Think of it like LIGOs. Set up one tunnel isn't enough to confirm a wave. You need two for comparison. In the same way, astronomers monitor two pulsars to detect shared fluctuations. If two pulsars show similar timing variations, the odds of random noise aligning perfectly to create this effect are incredibly low. Instead, it's far more likely that these pulsars are responding to the same gravitational wave passing through both. The photons from each pulsar may be riding this wave, revealing the subtle stretching and squeezing of space-time. By mapping these correlations, astronomers can build a picture of the stochastic gravitational wave background, uncovering a cosmic hum that echoes from the deepest reaches of the universe, helping us explore galaxy mergers, supermassive black holes, and even the echoes of the Big Bang itself. Astronomers have long sought evidence of a gravitational wave background, the faint hum of space-time, ripples generated by cosmic events across the universe. To find it, they've been analyzing pulsar pairs based on their angular distance in the sky. Here's how it works. If no gravitational wave background exists, we'd expect no correlation between the timing fluctuations of different pulsars. The data would form a flat line on a graph, hovering at zero. But if these pulsars are influenced by gravitational waves, their timing fluctuations should follow a distinctive pattern known as the Hellings and Downs curve. This curve would be the unmistakable signature of a gravitational wave background. And on June 28, 2023, after more than 15 years of continuous observations of 68 pulsars, the Nanograv team announced something extraordinary: strong evidence of this cosmic hum. Although there are noticeable error bars in the data, the results are statistically significant at the 3 sigma level. What does that mean? There's only a 1 in 1,000 chance that these results are due to random noise, a remarkable level of confidence. In physics, the gold standard for a discovery is the 5 sigma level, but 3 sigma is already considered compelling evidence. As more data is gathered, those error bars will shrink, bringing us closer to an official discovery. Right now, the collective noise from various sources is all we can detect. However, future advancements could allow astronomers to separate individual signals, pinpointing specific sources like supermassive black hole binaries. Imagine being able to listen to these colossal mergers and learn more about the universe's most dramatic events and even its very creation. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.